This is not an equation. This is an expression, right? So we can't divide by 3, but we can factor 3 out. Okay? So this is already different than what we've done before. This is the problem in college algebra. When college algebra is taught, usually by people who don't teach calculus, they don't realize that later on you need to complete the square when you don't have an equation. So it's better to teach completing the square, in my opinion, by this method. Get a coefficient of 1 here by factoring 3 out first. And James, I'm not going to ignore this. It's there. I'm going to keep it here the whole time. So when you pull out the 3, this becomes 4/3 x, and then this becomes 5/3. Do we all agree that that is algebraically the same expression? Yes. Someone have a question? I thought I saw a hand.
No? I was just going to tell you to factor out the 3. So you're just all going to do it on one side? Because usually when they teach completing the square, they have the equal 0, right? That's when it's
They have an equal 0 there,
yeah,
right?
That's when it's equation, and therefore you could that's when you could divide by 3.
That's right.
Sides. But I was taught just doing it on one side, how to complete the square on one side.
Then that might be a good thing, because that's what we're really doing. We don't have another side.
Right.
Yeah, we don't have. So everything we do has to be done here. So most students learn completing the square. You divide both sides by 3, and then at some point you add this thing to both sides. There's something we're going to come up with. You're going to add it to both sides. We don't have both sides. Okay, so that's why I'm going through this on the side, okay? Because this is important. Everyone good? Okay, what's the next step or procedure in completing the square?
We're going to have to take negative 4/3 and divide that by 2.
You take the coefficient on the x term, which is negative 4/3, and you divide it by 2, and then you square it.
Right.
Okay? So let's do that. We take, and this is just the standard way we do it, okay? You're going to take this coefficient, and you're going to divide it by 2 first. So I'm going to do that over here. I'm going to do it in blue. I take negative 4/3 and divide it by 2. So really, that's multiplying it by a half. That's the same as dividing by 2, which is negative 2/3. Okay, so in my college algebra classes, I actually call this the first magic number. Okay, this is one of the magic numbers we're going to use, and now we're going to come up with the second magic number, which we get by squaring that. Okay, we're going to square this now. Why? Because it works. Okay, square this, and when you square that, you get 4/9, and this is our second magic number. All right. Now this is where, again, most students are taught, what do you do with this number after you square? What do you do with it? You add it on both sides of the equation. Again, no equation.
Right.
Okay? So what we're going to do?
We're going to have to add it and then subtract it.
Add it and subtract it simultaneously.
So
So what we're doing is this, is we're realizing right here, right next to this x, there is a plus. Well, that's a great marker right there. There is a, there's a green one. There is a plus 0 sitting right there, minus 5/3. Now, believe it or not, this is a very advanced idea, okay? Like, for as long as you've been doing algebra, when we work with things, we've always been able to come in and multiply by 1. Like anytime we needed to maybe get a common denominator, we'd multiply the top by 3, bottom by 3, right? We could always do that because we're really multiplying by 1 and nothing changes. We've been doing that so much in our lives. We've never really taken an expression and just said, hey, that expression is exactly the same as adding nothing. But that's what we're about to do. But the nothing we put here is actually going to be this number and then take away this number. So let's do it. 3x squared minus 4/3 x. And we're doing what here? I'm going to add 4/9, and then I'm going to immediately subtract 4/9. And then I have minus 5/3 there still, right? Okay. Now this may look like a disaster, okay, but this is the way you have to do it if you have an expression and not an equation. Factor out to get a leading coefficient of 1. Take that number, divide it by 2, square it. Realize a hidden 0 right after that second term, and then rewrite that hidden 0 as plus that plus that number minus that number. Do not put minus then plus. It's plus then minus. And the reason why it's plus then minus is because what this does is it creates right here, these first three terms are automatically, by design, by the way we did this, that's called a perfect square trinomial. And this factor is guaranteed every single time that will factor. And you don't even have to think about what it's going to factor to be.
Because we have the magic number.
Yeah, we have the magic number. So this whole thing is going to turn into this. 3 out front, okay, parentheses. These three terms turn into another set of parentheses and then squared. And what it's going to be is x
Minus 2/3.
and then that number. The first one, not the second one. So minus 2/3.
Plus or minus 4/9.
And now, yeah, now you have to say, we have to put these two numbers together. Okay? So we have to get a common denominator there.
That's going to be.
What is that? I can't. This is literally where my brain just stops. It just says, I don't want to do this.
So that's going to be 12 minus 40 over 9. And then that's going to be.
Minus 19 ninths? Negative 19 over 9. Yes? Okay. So this is minus 19 over 9, close parentheses. Now I know that some of you might wind up in the tutoring lab at some point for this, and you might go up to a tutor, and they may do this a slightly different way. And what I want you to know is that I'm showing you this way because I think that this benefits you long term. Okay, more than some method that might get you there faster. All of the little algebra, no pictures please. No pictures please. No, I'm kidding with you, James. You got it? All the little algebra and this hidden zero and all that, like these to me are like big things that will come up later, especially for any math majors in here. This is like a huge deal because you can add and subtract functions. You can add and subtract integrals, and that hidden zero is there all the time. All right, there it is. There it is. Okay? We can rewrite. Now, this was your idea. Why did you want to do this? It's going to work. Okay? So let's go back here. You ready? We're going to come back to this now, and we're going to rewrite this integral. This integral now becomes the square root of 3 parentheses, then another parentheses, x minus 2/3 squared minus 19 ninths, and then, yeah, dx. That's it. There's nothing else for us to write. Now you see that 3 out there that we factored out? See that 3? Can we take it out of the root? It's going to come out as a root 3. So because we have multiplication here, we can do the root of the 3 by itself times the root of that stuff by itself, right? But the root 3 that's by itself, I'm going to just bring it out of the whole darn integral. And now I have this. Finally. I don't need this parenthesis anymore, sorry. So because this root 3 came out, or because this 3 came out, I didn't need that big set of parentheses anymore. Now we kind of, like if you squint your eyes enough, don't we kind of look like variable squared minus a squared? Like variable squared minus a squared? All right, let's do a quick u sub. Just a quick u sub. We're going to let u be this. Okay, let's see what happens. If u is equal to x minus 2/3, what's du?
It's going to be just dx.
Just dx, right? So let's see how we can rewrite this then. This will become root 3 integral square root of, okay, this right here is u squared, right? Minus 19 ninths. And then we have times dx, but dx is du. Now, doesn't this look like the formula? But instead of x, we have u. So this looks like u squared minus a squared, right? U squared minus a squared. So what is the trig sub that we do when we see variable squared minus a squared? A secant theta. Okay, what is a for us here?
Negative root 3 over 3. Negative root 19 over 3.
Yeah, so a for us is the square root of that number, which you can do the roots separately. Root 19 over
3.
root 9, which would be 3, right? Do you all agree that that's what a would be?
Yes.
It's just the square root of that number. It's ugly, but that's what it is. And then what did you tell me the substitution was going to be?
Secant theta.
A secant theta. Now, I'm replacing what with a secant theta?
X or U.
U, okay, because we switched from x to u. So now we're going to say u is equal to root 19 over 3 secant theta. Isn't this fun?
Yeah.
Weren't you promised a mess? A lot of things to keep track of, right? Didn't people tell you this is the way it would be?
Still seems to be step by step.
Yeah, but I'm saying as far as you're going to have to put this all together at some point, right? And do it all. All right. What now?
Then we find,
What's a derivative of this now, right? So what is a derivative of this? This would be on your formula sheet, wouldn't it? It would be a secant theta tangent theta, but you know that by just taking the derivative. A secant theta tangent theta d theta. What else do we need to have an idea of here? What the root turns into. What does this ugly root turn into when we make this substitution? So this is where, again, we could derive it, couldn't we? But we could also memorize it. And this is the one we're talking about. Whenever you make the substitution, we're using u, not x, right? Whenever you do a secant theta, here's what the derivative is, but that big ugly root thing turns into a tan theta. Okay? So we know that, I'm running out of room over there, so we know that the big root thing, which was u squared minus 19 over 9, we know that that turns into root 19 over 9, or no, over 3 tan theta. Okay, so if you're looking like these are the, this, and this are the three things that I need in order to rewrite the whole integral over again. Okay? You all ready to rewrite the integral? Any questions? Okay, here it comes. Here's the integral we're rewriting, right? So root 3. And all we have here is what? This ugly root thing, which is root 19 over 3 tangent theta. And that's it? Times du. And what's du? Root 19 over 3 secant theta tangent theta d theta. Those, you're, okay, where? What do you need me to do? Okay, so that came from, okay, you're good with this? That's the root 3 out front, right? Okay, this right here came from this right here. Are you comfortable where this came from? Sorry if you're not.
Yeah, with the substitution.
Yeah, if you put that thing back in here, like if you plugged in root 19 over 3 secant theta right here, you would go through and you get a Pythagorean identity, and eventually you turn into this. I suggest you memorize it. We'll run through them again after I finish this problem, the things I think you should memorize. But This is what we get, okay? So then when we go to rewrite the integral here, we know that that big root thing becomes that, right? So that's this. But then we also have du. But du is, from this substitution, we said du would have to turn into this. And that's this piece right here. Make sense where it all comes from? Okay. Root 19 times root 19 is 19, and then the 3 times 3 on the bottom is 9. That's all going to come out. So 19 root 3 over 9 integral tan theta squared, tan squared theta, times, oh shit, I see what's going to happen here. Secant theta d theta. Yep, I see what's going to happen here. This ain't going to be pretty. So here's the problem. Here's the issue. I'm hoping for a basic u sub here, right? So if I let u be tangent, then the derivative tangent is secant squared, but I don't have secant squared. So if I let u be secant, I need the derivative of secant is secant tangent. I've got tangents, but I don't have any more secants.
So we're going to have to write them in terms of
You could go sine and cosine, yes?
Could you replace the tangent squared with 1 minus secant squared?
Yeah, and that's what I didn't want to happen, but I think that's what we're going to wind up doing. So we can, you could probably go either way, with the sine and cosine or this way. Let's rewrite this using the Pythagorean identity, which means, what does this turn into? Secant squared theta minus 1. That's what that is. So this becomes 19 root 3 over 9 integral. Okay, so I have a secant squared theta minus 1 right there, right? In place of this. Distribute the secant through it. Secant cubed theta minus secant theta d theta. And if you look back in our notes, I did both of those problems in class. I did secant by itself, and I did secant cubed. Now, we have a formula for this one. That's on your formula sheets. It's on your formula sheets. Now, we derived it ourselves, and there was the problem where I said someone came up with this, and you would never come up with this on your own, but they did, and it's pretty cool that it works. We don't have to go through that work again. We just need to go straight to the formula, all right? Secant cubed, just double check. I do not believe that's on your formula sheets.
Wait, secant cubed?
Secant cubed. Not on the formulas that I provide you.
Oh, so.
I mean, they are in the back of the book on.
Oh, so our notes, you mean?
Well, it's not on the formula sheets, though, right? It's not. So, yes?
We take out like a secant and then add a secant squared.
If you take out a secant, have a secant squared. Well, that's where we came from, right? We had this initially, right? And then we had the secant out here. The reason why you can't do anything with this is because if you let u be secant, that's not the derivative. And if you let u be secant here, that's not the derivative. So there's really, I don't think there's any way around this. We've got ugliness here, pure ugliness.
Are you talking about the secant cubed x?
Yep,
And then
we did that with integration by parts.
Yeah,
And we got a final answer, right?
yeah.
I'm about to use that, so you're going to have to tell me what it is, okay?
Okay. Oh,
All right.
gosh.
So do you appreciate how much work this still would have? You would have to do like an integration by parts like that, on the side.
So you're gonna so you would have to do an integration by parts.
Mhm.
Okay, because that's what we did here.
Yeah. Now on a test, I would probably not give you, well, I know I wouldn't give you anything like this where you would have to go do secant cubed, all right? I would just tell you, I would give you like the formula for secant cubed, so that way when you got to it, you would just have it, all right? But we're here, so we're going to continue this. We've come too far. How many problems have we done today? This is the third one?
Yeah.
And we're almost out of time. You know, we only have 20 minutes left. This gives you some idea of how long these problems are, right? Mm-hmm. We're going to get through 3 of them today. That's about it. Okay. All right, so here's where we are, right? So y'all need to help me out here. So we have 19 root 3 over 9. Okay, the integral sign's gone, right? The antiderivative of secant,
It's one
this
half.
one?
It's 1/2.
So 1/2
Secant times secant x. Secant,
secant, we're going to use theta because everything's theta here.
oh, secant theta
Secant theta
times tangent
times tangent theta
plus 1/2 times the natural log of secant x plus, I'm sorry,
Secant theta.
sorry.
all right.
Plus tangent theta. And then.
That's
yeah,
it for that one,
plus
right?
C, yeah.
Okay, so that is using what, do you all agree with that? Does everyone have that? Yes? That is the antiderivative of that. Okay, minus, right? Minus the antiderivative of secant theta, which turns out to be
The natural log of secant tangent of theta plus 2,
secant theta
tangent theta,
plus tangent theta?
no, times tangent.
Is it times tangent?
Plus.
It should be plus. Yes? Okay, all of that plus c. Those are the same, aren't they? Natural log secant theta plus tangent theta, those are both the same, aren't they?
Yep.
You have a half of this natural log minus a whole natural log, which leaves you with minus a half. You understand?
Wait. Yes.
Yes, these are like terms. They're just
Right, so yeah, it's a half plus a whole.
okay. So I'm gonna do that on my next line. So 19 root 3 over 9. Let's see. I'm gonna have a half on both of them, aren't I? I'm gonna have a half on this one's gonna half, and then this one's gonna turn in. Really, this is gonna turn into a minus, right? And this one's gonna go away. Right? That's what's gonna happen. So I'm going to actually pull the half out of both of those right now.
Okay.
So what does that become? 19 root 3 over 18. And then secant theta, tangent theta, minus natural log of secant theta plus tangent theta plus c. Done. No. Got to get it back to x now. But we got to get to u first. Yeah, u before x. So the relationship we had with theta was that we made a substitution way back when that u is equal to
X minus 2/3.
no, that was a different one, right? This is radical 19 over 3 secant theta, right? Wasn't that what we had?
Yeah.
That's what we had earlier. That's what we had earlier. This was our trig sub that we did, right? So I need to figure out what the triangle looks like for this. So this is going to be 3u over root 19, multiplying both sides by the reciprocal, secant theta. Hogan, I can hear you asking me again why we need to do this real world. I can hear it. And it's like how far down the hole can you go, right? Without your brain just starting to give up on you. You know what I'm saying? Like, can you keep all this together? There's a couple of spots in this problem where you could have made a mistake, yeah?
Yes.
Right? So that's what it's about. It's like how much can you do like without making mistakes? And I mean, I understand mistakes are going to happen, but you know, you want to be able to go through a problem that takes you 45 minutes and be, you know, just keep grinding away at it. Yeah, okay, let's go. So that, I draw my triangle. All right, secant is the reciprocal of cosine. So that should be that's not adjacent over hypotenuse, that's hypotenuse over adjacent, right? So this is 3u and this is root 19. And so this side should be the square root of 9u squared minus 19. I know y'all are going to look at that and be like, what the hell? We've never seen that before. Like, that looks wrong, right? Do y'all agree that that looks not like what we had before? Don't freak out, okay? Don't freak out, because you know how I did this right here like this? I could have, if I wanted to, have done, let me see, here. I could have put this constant right here like this. Like, that would have been the same thing. Then I would have called this side u and this side what? Root 19 over 3. And then if you do it, you get u squared minus 19 over 9 or whatever it was. I'm just saying, don't freak out. Like, yes, you're freaking?
Yeah, that's what I was asking earlier.
Yeah.
Remember?
Mm-hmm. And I said most of the time you should see that here. But that shouldn't be a thing that you're like doing anything right or wrong. I don't want that to be like, okay, I got to it, I'm good. Because like I said, there's a lot of work that's completely independent of this triangle. Are we okay going off this? All right. Let's get back to this. All right, so we're here. We have 19 root 3 over 18, parentheses, secant theta. And I think I want to write this back the way we had it. This was like this, right? Look at secant theta. We actually know it, right?
Right.
It's just 3u over
19.
over root 19. Okay, times. Do we know what tangent theta is? This over this, right? Okay. So root 9u squared minus 19 over root 19. Okay, that's the first part. Minus natural log of secant theta. We know that. 3u over root 19. Plus tangent theta. Well, we just did tangent theta. So that's going to be root 9u squared minus 19 over root 19.
Right.
And then close that plus c. Last step. Replace all of your u's with x minus 2/3. And then we could also clean it up a little bit. There's some algebra we could do. Let me see, what algebra could we do?
We could add those fractions.
We could add those fractions over there. We can multiply those two together and get 19, right? And we could add these two, put the numerators together. That's okay. So here's going to be this. I think this is as far as I'm going to go. Okay, so we've got 3u, but u is x minus 2/3.
Right.
Was it 2/3? Yeah.
3x minus 2.
3x.
X minus 2/3. That was
Yeah,
what we
That
did
is
for you.
3x minus 2.
Oh yeah, if you distribute, yes. I'm just slapping it in there for now. And then we have 9, and then x minus 2/3 squared minus 19, and then all of that over, the whole thing over 19. Minus the natural log of 3 times x minus 2/3 plus the square root of 9 times x minus 2/3 squared minus 19. All of that over root 19 plus c. Shall we check it? No, we won't check that. That would be a hell of an exercise to check that, right? How could an integral that simple looking turn into something that bad, right? Right? I mean, it was just the square root of 3x squared minus 4x plus 5 or whatever, minus 5. Or why are things so bad? So let's go to Wolfram alpha. Can we do that? Let's see what Wolfram alpha tells us the answer should be. Now, I'm not expecting Wolfram alpha, the answer here, to look like mine. Integrate. Okay, what was it? Square root.
Of 3x squared minus 4x minus 5.
Minus 5. Okay, here we go. Let's see how long it takes Wolfram Alpha to do this.
And we crashed.
There it is. Okay, I'm happy to see logs. Happy to see logs. There's the answer. So look at this expression right here. This right here. Can y'all see that okay? Looks like ours could turn into that, yeah? Like if you distribute the 3 through here, you get 3x minus 2. Well, that's that, right? And then do you believe that if we started expanding that out and putting it together, we might get the original root back in there somehow? I think we're going to have to play with these constants, though. Like these constants, was that an 18? Yeah, it was. These constants are going to somehow, yeah, like the 19s are gone and some things should happen. I think that matches up pretty good with what we have out front here, yes? And then we have minus, and then we have a log, right? And then the log has the root, and then this piece here. So I feel good that we're there. It would be an algebra exercise to show that those two are equivalent. Yes?
Quick question.
Yeah, go ahead.
Might be stupid.
I've heard there's not stupid questions, but I disagree with that. I think there are stupid questions. I don't think you're going to ask one, but I mean, haven't you ever had someone ask you a stupid question?
Yes.
Yes. Okay.
What if
Yes.
you put the whole function in parentheses and put half, power half, and then substitute the half to everything, and then use the power rule?
Oh, okay. I think I know what you're saying. Well, then that would make it easy, wouldn't it? Yeah, but you can't do it algebraically. So I think what you're saying is, yes? I think what you're saying is this, and I could be wrong. I don't know. Is this what you're saying?
No, put the whole thing in power half.
Okay, put the whole thing to the half power. And then apply the half to each one? Okay, that's the same thing I was doing just now. So what you're saying, what you're suggesting is this. You want to make this go to here, here, and here, right? Which it means you want to do the square root of 3x squared, you want to do the square root of something else, square root of something else, but you want to separate those with either addition and subtraction, right? Okay, so you can't do that, and the reason why is because we have these properties. This is a good question. So let's look at this. Let's say we have a times b times c, and we want to raise that to the n power. So this is equal to a to the n times b to the n times c to the n. Because you have multiplication between these, this works. It's when you put addition in here that it doesn't work. So if you have addition or subtraction between your expressions and you raise it to the n, unfortunately, man, God, life would be so good if this is the way it was. Like literally, math would be so much easier if things worked like this. Okay, but it's not true. And how could you check? Just give yourself an example. Think of that squared. Okay, so on one hand, this is just 3 plus 3. This is just 6 squared, right? Which is 36. But let's try doing it the other way. So is this question mark, is it that one squared plus that one squared
4.
plus that one squared? So that's 1 plus 4 plus 9. What's that? 14, right? So 9, 10, 4, yeah, 14. Do you see what I'm saying? So you cannot, because it was addition subtraction, you cannot break it up individually. Sorry. It's just the way it is. That's what makes this so hard, right? Is that it's not hard, but just challenging, right? There's so much we had to do right there. A lot of algebra, right? All right, we only have 5 more minutes, and there's not a whole lot more I can do. I can't like say, let's look at one more problem. I think now you can maybe have an appreciation for how long this homework set should take you.
gosh.
This homework should take you quite some time. Yes.
You were gonna go over the list of things that we probably should remember.
List of things.
Because remember you were saying that we should remember, like, when we're going, like, we're.
Oh, yeah, yeah.
taking our
Okay, yeah. Not. I knew I said that, but I couldn't remember what I was saying that about. So let's just run through them real quick. If you see this, and let's try and see if we can do this without cheating off of your cheat sheet. If you see this, okay? Let me tell you what I think when I see this. I think of the Pythagorean identity. The Pythagorean identity, sine squared plus cosine squared equals 1, that right there. If you solve this for sine squared, you get that, right? Okay. So when I see this in my mind, I'm actually thinking 1 minus cosine squared. 1 minus cosine squared. And what's 1 minus cosine squared? Sine squared. So this is like the square root of sine squared. So this makes me think I'm going to be using sine. I'm just telling you how I do it, all right? So I see this and I automatically know x equals a sine theta is going to be my substitution. That's the first thing I put down. Second thing is just take the derivative of that. So the derivative of this is a cosine theta d theta. And now how do I remember the root part? Same thing I just went through. This is like 1, right? 1 squared. 1 minus what's x? Sine. So this is like 1 minus sine squared, right? Which is cosine squared, but then square root. So this should just turn into what? A cosine theta. Does that help at all? I don't know. I mean, everyone's kind of different. I'm seeing this. I'm seeing 1 minus cosine squared, and that means I'm going to be using sine as my trig sub, and then there's a derivative, and then, like I said, this is going to turn into cosine because if this is sine, 1 minus sine squared is going to be cosine.
No.
No?
No.
Then you just have to memorize it.
Okay.
Yeah. Okay, let's look at the next one. The next one is, let's do them this way. Okay, so when I think of trig identities, again, I'm treating this like the 1. Which of my Pythagorean identities has 1 plus something squared?
Wait,
1 plus secant squared. 1 plus something squared is 1 plus tangent squared equals secant squared, right? 1 plus tangent squared equals secant squared.
Yeah.
That means I want to replace that x with a what? 1 plus tangent squared. So I want to replace x with a tan theta, right? The tan theta, thank you. The derivative of that, well, that I just know from Cal 1. This is just secant squared theta d theta. And then what about the square root of all that stuff? Well, I said this is going to look like 1 plus tangent squared. 1 plus tangent squared by the identity turns into secant squared, but then you're taking the square root, so that's just secant theta. Does that make sense?
I see what you mean when you say, like, look at it in terms of, like, the Pythagorean.
Mm-hmm.
Like, seeing, like, okay, well, what is that, you know? As
Yeah,
far
like
as,
which of these does that look most like?
Right. It was,
Yes. I'm missing the A, thank you.
I see what you mean.
So let's look at the last possible one. The last one is the other way around. X squared minus a squared. So this one's a little tricky, but think of your trig identities where you would have the trig thing squared minus 1.
That's tangent squared theta minus 1. So it'd be
So
secant squared
tangent. So yeah, you go back and look at this identity. You have tangent squared theta plus 1 equals secant squared theta. So if you were to take this and try and make it look like that over there, you need to move the 1 over to this side, wouldn't you? And then it would look like this. Tangent squared theta equals secant squared theta minus 1. So you have a trig, something trig squared minus 1. The x is always your trig thing. The a is always like the 1. So this is some trig thing squared minus 1. And that's this, right? So what is your x going to be here? It's the trig thing that's here, which is secant theta. Dx would be just the derivative of that, a secant theta, damn it. A secant theta. And then derivative of that would be a secant theta, secant theta tangent theta, d theta. And then what would that root ugly thing turn into? Yeah, if this is secant squared theta minus 1, then that's really tangent squared theta, and you take the square root. So this should turn into a tan theta.
So you would see your x, in terms of
Your trig function,
and
yep.
then your a as your constant.
As your 1, yep. I hope that helps. I mean, otherwise you just have to memorize them just like a non-thinking, just memorize, you know? All right, well, I encourage you to do your homework. Do you understand now it's going to be harder for me to give you quizzes? Like, I can't give you a 40-minute quiz over a problem. Do you all understand that that becomes very hard for me to give you something in class, but I'll still find ways of doing it. I don't know, I might give you some problems and just ask you, like, you know, hey, what's the trig sub that you're going to use here, right? Like, get the integral at least set up, and then, you know, at some point I just, you know, tell you stop. You can't go the rest of the way.
Okay.
So another, like a quiz next week might be just, I give you the integral, ask you for the trig sub, set up the integral in terms of theta, and stop.
Okay.
You know? Yes?
The test for these kind of things, is it like 5 questions?
Yeah, your next test isn't going to have a whole lot of problems on it. Yep. Because one problem will address many different topics. Especially when we get to the next section, like partial fractions. You might have one partial fractions problem where in that problem, you first have to do the partial fractions part, but then in that you might actually have to do a trig sub, which then might require u sub. So it's just everything together in one sort of, kill 10 birds with one stone. Let me turn my camera off. Yeah, they're long. Have you started working the homework on these? Okay. This 6-2? Yeah, this is a monster section in terms of homework, but